for this one, roots are difficult. Ten, yep. -5, 10, 20. These two are worst problems actually, because though the rest of the thing is very simple, we need a lot of time just to find the roots, right? Of course, when you use calculators, at that time it is possible that we can directly solve the cubic equation. So that's the star mark. So you put the coefficients, you will get the roots, and we do the formality, synthetic division, and proceed further. Okay, and we are allowed to use calculators, but we don't have calculators right now, so we had to struggle, right? Otherwise, till cubic there should be no problem. Okay, if it is 4th degree, but in eigenvalues, eigenvectors, we don't have 4th degree, so our job is simple, right? So we proceed with the next part. You can do this. So these are roots are lambda values are -5, 10, and 20, right? Let us try the next one. It is 1 minus 6 minus 4, 0, 4, 2, and 0 minus 6 minus 3. Now, 2 of you were absent last time, so what we are supposed to do is, given matrix A, to find eigenvalue we will have the characteristic equation as mod of A minus lambda I is equal to 0. Now lambda is just a scalar quantity, and so when we subtract A minus lambda I will be only the identity matrix, so 1 0 0 0 1 0 and 0 0 1, and when you multiply by lambda it will be lambda 0 0 0 lambda 0 and 0 0 lambda. When you subtract it from A, only the diagonal elements will get subtracted, rest of the elements will remain as they are, and we are required to find or form the determinant of it, which will result in the cubic equation in lambda. And for that we have the equation as lambda cube minus S1 lambda square plus S2 lambda minus mod A equal to 0. What is S1? This is sum of diagonal elements. S2 is sum of minors of diagonal elements. So here it is lambda cube minus sum of the diagonal elements is 1 plus 4 minus 3 lambda square, plus these are going to be the minors of the diagonal, so it is 4 2 minus 6 minus 3, plus minor of this 4 will be 1 minus 4 0 minus 3, and minor of this minus 3 will be 1 minus 6 0 4 lambda, and plus the value of the determinant, it will be 1 into bracket 4 2 minus 6 minus 3 minus plus 6 into bracket 0 minus 3 minus 4 into bracket, it will be again 0 4 0 minus 6 equal to 0. So this will reduce to lambda cube minus 2 lambda square plus into bracket, this is minus 12 plus 18, so 6, this is minus 3, and this is plus 4 lambda, and mod will come out to be minus 12 plus 12, 0 आता है ना ये, minus 12 plus 12, 0, minus 12 plus 12, 0, minus 0 equal to 0. So we get lambda cube minus 2 lambda square plus lambda equal to 0. So it is lambda into bracket lambda square minus 2 lambda plus 1 equal to 0. So lambda equal to 0 and lambda minus 1 bracket square equal to 0. So we get lambda equal to 1, 1. Now this is the first case where the eigenvalue is repeating. Up till now we never had any problem where the eigenvalue was repeating. All the three values were different. Now for the first part, that is at lambda equal to 0, we will get the equations as, put lambda equal to 0 in this, so it is 1 minus 6 minus 4, 0 4 2, and 0 minus 6 minus 3, x1 x2 x3 equal to 0 0 0. That is how we proceed, and we are supposed to take two equations. You observe that these two equations are just the same, right? If you take 2 common and minus 3 common from here, they are same, so we are not interested in them. We take first two, so it is x1 minus 6x2 minus 4x3 equal to 0, and 0x1 plus 4x2 plus 2x3 equal to 0. So it is x1 upon minus 6 minus 4 4 2 equal to minus x2 upon 1 minus 4 0 2 and equal to x3 upon 1 minus 6 0 4. So it becomes x1 upon minus 12 plus 8, so it is minus 4 equal to minus x2 upon minus 12 plus 16, so plus 4, minus 12 plus 16 plus 4. This will be 2 2, and this will be x3 upon 4, and so we get the first vector as actually 4 2 4. After taking 2 common, it will be 2 1 2, 2 minus 1. Yeah. So till this there is no change. The change will begin when we substitute lambda equal to 1. If we put lambda equal to 1, it becomes 0 minus 6 minus 4. It will become 0 3 2, and this will become 0 minus 6 minus 2, and practically all the equations will come out to be same, and then the things begin, right? So make a note till this point, and we'll pick up from lambda equal to 1 the repeated root. Okay, for the time being, just observe that this was not symmetric. This was not a symmetric matrix, because it will matter on that whether the matrix is symmetric or not. Okay. So done till this point? Yeah. Now, at lambda equal to 1, so lambda 2 equal to 1, we get it as 0 minus 6 minus 4, 0 3 2, and 0 minus 6 minus 4, operating on x1, x2, x3, and we get it as 0, 0, 0. So we just have the same equations. You take any equation, it will be simply 3x2 plus x3 equal to 0. 2x3 equal to 0. But still it will be 3x2 equal to minus 2x3 and x2 upon 2 equal to x3 upon minus 3. But what about x1? 0. We don't have x1 at all. It can take any values, yes. But then what is the conclusion? Because you will have to just look back, and we had got mod A to be equal to 0. Does it indicate something? When mod A is 0, what does it mean? Inverse does not exist, right? But then in reality these are the homogeneous equations. In reality these three equations are homogeneous equations, and being homogeneous equations, they will have trivial solution only when mod A is not equal to 0. So mod A is already 0. So what is the conclusion? In that case it will have infinite solutions, right? That is one conclusion we have. Now we will have to remember, just make a note, write down. When the matrix is not symmetric, when the matrix is not symmetric, the vectors, the eigenvectors will be linearly dependent. The eigenvectors will be linearly dependent. So what should we do now? We have reached this point. What should we say? Or it can be any value that we can take. Can we say that this is same as x1 upon 1? How does it matter? Or x1 upon 2 or x1 upon 3? Will it matter? No, because, and even if it is 0, it will not matter. But what condition he is specifying is they should be linearly dependent. So we will have to keep in mind that also. Okay, x1 turned out to be 2 minus 1, 2. x2, if we are planning it to be something like 1, 2 minus 3, then what would be x3? So that they will be linearly dependent. So that they will be linearly dependent. Unfortunately, we did not get 3 variables. If we get 3 variables, job is very simple. I assume 1 to be equal to 0, I get the relation between other two. Then I assume y to be equal to x2 equal to 0, I get the relation between them. And it happens automatically. I don't have to do anything for that. Here, as we have equation only in 2 variables, that's why it is creating a problem. Now suppose the next third vector I write it as I am allowed to have anything, will they be linearly dependent? Did you get the question? Can we prove that these are linearly dependent? Linearly dependent, the condition is C1 x1 plus C2 x2 plus C3 x3 should be 0. So will it turn out to be 0? Can you tell me any such relation? The relation is very obvious here. Just think. Can we set some relation between x1, x2 and x3? We can't. Okay, then remember that this value can be assumed as anything, and then solve this problem separately to find the relation. We know how to find the relation between, though we don't have to write it in this case, but in such a case x1 can take any value as long as we have these two values identical. This value will not matter. It can be anything and still it holds good, and they will be linearly dependent. But this particular method you will have to go other way around to find out whether these are linearly dependent. That is itself a separate problem. So far as the procedure is concerned, we can say that, and again I am telling you, this became a difficult problem because we did not have x1, right? And if we had x1, then what will happen? You can always see that it is 0 x1, right? But still we don't have two equations. So what do we do with this 0 x1? If we had two equations which are not identical, still I would have solved it. But as the two equations come out to be only one, and that's why we will have to find out the third vector. Okay, make a note. There are three eigenvalues, 0, 1, 1. That is the problem. For 0 there was no issue. For lambda 2 equal to 1, we got one vector, and this is lambda 2 equal to 1, and this is also lambda 3 equal to 1. And we don't get two different sets of equations. That is a problem. We get, and we did not. Had it been that these are three different equations, I could have taken only two combinations. I am through. But I am not getting that. I am not getting two equations also. I am getting a single equation from which I get a relation which is just this. Okay. So I know that for lambda 2 equal to 1, x2 and x3 proportionate roots are going to be 2 and minus 3. The question is, what should be x1? Make a. Unfortunately, we took the first problem, which itself was a bit difficult. Next problem, let us hope that this gives us equation with 3 variables. Let it be a single equation. So here characteristic equation is mod of a minus lambda I equal to 0. So it is minus 17 minus lambda 18 minus 6 minus 18 19 minus lambda minus 6 minus 9 9 minus 2 minus lambda equal to 0. So it is again lambda cube minus sum of the diagonal elements minus 17 19 minus 2 plus it is 19 minus 6 9 minus 2 plus it will be minus 17 minus 6 minus 9 minus 2 plus it will be minus 17 18 minus 18 19 Oof. Lambda minus 17 into bracket minus 38 9 54 plus 54 minus 18 into bracket 36 minus 54 minus 6 into bracket 162 minus 162 plus 171 equal to 0. Lambda cube minus 0 lambda square plus 38 plus 54 plus 17 34 वजा 54. हाँ यही किया था मैंने 323 plus 324 lambda I missed out this minus 17 into 16 minus 18 into minus 18 minus 6 into 9. So lambda cube minus 0 lambda square 135 minus 3 lambda, and how much is this? This is 324, which is plus, this is minus 54 and 262, but 272. So minus 54, this is 270 minus 2 plus 2 equal to 0. Oh, इतना कुछ करके, so it is lambda cube minus 0 lambda square minus 3 lambda plus 2 equal to 0. Sum of coefficients is 0. So what will be the root? Minus 1. So root will be plus 1. So we have lambda minus 1 into lambda square plus lambda minus 2 equal to 0. So lambda minus 1 into lambda plus 2 into lambda minus 1 equal to 0. So we get lambda equal to minus 2 1 1 as 3 eigenvalues. Out of that, lambda 1 equal to minus 2, the equations will become, so minus 15 18 minus 6 minus 18 17 minus 6 and minus 9 9 0 x1 x2 x3 is 0, 0, 0. Take the different root, different eigenvalue and solve for that. And it is better that we take these two equations or these two rather than entering into this calculation. Second and third. Okay. So minus 18x1 plus 17x2 minus 6x3 equal to 0 and minus 9x1 plus 9x2 plus 0x3 equal to 0. So we get x1 upon 17 minus 6, 9 and 0 equal to minus x2 upon minus 18 minus 6 minus 9, 0 equal to x3 upon minus 18, 17 minus 9, 9. So it is x1 upon 54 equal to minus x2 upon again 54 minus 54 and then x3 upon it is minus 18 into 9, so minus 162 plus 153. So we end up with getting finally it as x1 upon 54 equal to x2 also upon 54 equal to x3 upon minus 9. So it is x1 upon 9 chopan, so 6 equal to x2 upon 6 equal to x3 upon minus 1. So lambda 1 equal to minus 2. Capital X1 is 6, 6 minus 1. First, second घेतल्यावर वेगळं येते का आन्सर? Oh, then everything goes wrong. तो इथे है ना, it was minus 19, it is 21, this becomes 21, this is 21, this is 21, so this will change. It is 189, na? $189, so 27. That 2 plus. If it is plus 27, then I can write it as 221. Sorry, it was minus 19 plus 2. And then at lambda 2 equal to 1, the equations will be minus 18, 18 minus 6, minus 18, it will be added, plus 18, minus 6, minus 9, 9 and 1, x1, x2, x3 equal to 0, 0, 0. Minus 3. all the three equations come out to be same. So the equations are minus 18x1 plus 18x2 minus 6x3 equal to 0. So minus 3x1 plus 3x2 minus x3 equal to 0. We will have to comment here and say that as matrix is not symmetric and eigen values repeat, the vectors must be dependent. So we have minus 3x1 plus 3x2 plus minus x3 equal to 0. For first vector I can assume that let x3 is equal to 0. And so I get minus 3x1 plus 3x2 equal to 0, or 3x3 equal to 3x1 x2, 3x1 equal to 3x2, and so it is x1 upon 1 equal to x2 upon 1 equal to x3 upon 0. So the second vector comes out to be 1 1 0, and I can assume let x2 to be equal to 0. So I get minus 3x1 minus x3 equal to 0. So it will be minus 3x1 equal to x3, or x1 upon 1 equal to x2 upon 0 equal to x3 upon minus 3. And so the third vector comes out to be 1 0 minus 3. It is easier when we get all the three variables in the final equation, because we can assume one of them to be 0. If we get two variables only, then the third one is to be assumed, and that can be randomly anything. We have assumed last time 1 and 2. It can be 1 and 3, 1 minus 1, whatever. What was the answer? One 1 0 and 1 0 minus 3. It could have been other way also, 0 1 minus 3, if x1 is assumed to be 0. Find eigenvalues and eigenvectors for two 1 1 1 2 1 0 0 1. And minus 2 2 minus 3, 2 1 minus 6, and minus 1 minus 2 0. Again in the same type, eigen value is going to repeat. And the procedure will be different if the matrix is symmetric. So these are non-symmetric matrices. When eigenvalue repeats, the vectors will be dependent. In this chapter, the problem statement remains the same, and it says that find eigenvalues and eigenvectors, and there are so many different cases, so it becomes a difficult task. take this one. It is 7, 0, minus 2, 0, 5, minus 2, and minus 2, minus 2, 6. Find eigenvalues and eigenvectors. Now only change from the previous two cases, the very first and this previous one, they were non-symmetric matrix, and first case was when eigenvalues were non-repeating, second case eigenvalues repeating. Now we have a symmetric matrix. Now let us see if the procedure creates some problem for us because of the symmetry. 3 eigenvalues we find out. If they are different, then let us see how to proceed. If we get stuck up, then we will have to think. If we don't, then the procedure is same as non-symmetric. 3 different eigenvalues, 3 different eigenvectors. Tell me the equation first. अलग symmetric है तो लक्षात. So here at lambda 1 equal to 3, the equations will be 4x1 plus 0x2 minus 2x3 equal to 0, and 0x1 plus 2x2 minus 2x3 equal to 0. I am taking the first two. So it is x1 upon 4 equal to minus x2 upon minus 8 equal to x3 upon 8. And so capital X1 comes out to be 488, which is as good as 1, 2, 2. At lambda 2 equal to 6, equations will be x1 plus 0x2 minus 2x3 equal to 0, and it will be 0x1 minus x2 minus 2x3 equal to 0. So it will be x1 upon minus 2 equal to minus x2 upon again minus 2 and equal to x3 upon minus 1. So capital X2 will be minus 2, 2 minus 1, or 2 minus 2, 1. And at lambda 3 equal to 9, equations will be minus 2x1 plus 0x2 minus 2x3 equal to 0, and 0x1 minus 4x2 minus 2x3 equal to 0. So it will be x1 upon minus 8 equal to minus x2 upon 4 equal to x3 upon 8. So capital X3 comes out to be minus 8 minus 4, 8, which is minus 2 minus 1, 2. Now if we multiply these two, it is minus 2 plus 4 minus 2, 0. This into this, it is minus 2 plus 4, 0. This into this, 4 minus 2 minus 2, 0. So vectors will be orthogonal, is the property. Meaning that for symmetric or non-symmetric and eigenvalues non-repeating, the solution procedure is straightforward. Okay, in one case they come out to be dependent, in other case they are orthogonal, but that is fine. And now our case number 4, A is symmetric and eigenvalues repeating, and property remains that they are going to be orthogonal, and so we will have to have a different procedure to solve them. It is 6 minus 2, 2, minus 2, 3 minus 1, and 2 minus 1, 3. We need to observe before proceeding whether the matrix is symmetric or non-symmetric. Here it is symmetric. It is characteristic equation. I am showing you the procedure how you should write it in the exam, and you can speed up of course later. It is lambda cube minus s1 lambda square plus s2 lambda minus mod a. So it is lambda cube minus 12 lambda square plus 8 plus 14 plus 22. 18 plus 4 plus 14, it is 18 minus 4, 14. Third is 18 plus 14 minus, it will be 6 into bracket 8, so 48 minus 2, it is minus 6 plus 2 minus 4 into 2 plus 8. 1 second. Minus minus plus 2, it is minus 6 plus 2 minus 4, and outside it is plus 2 minus 8, and the last one will be 2 minus 6 minus 4 and again minus 8. Lambda cube minus 12 lambda square plus 36 lambda, and this is minus 32. Is this right? Sum of odd even are not 0, overall it is not 0, so we will have to try with 2 minus 2, so it is 1 minus 12, 36 minus 32, 2, 1, 2 minus 10 minus 20, 16, 32, got it. So it is lambda minus 2 into lambda square minus 10 lambda plus 16 equal to 0. That is lambda minus 2 into lambda minus 2 into lambda minus 8. So we get lambda as 8 to 2. I prefer to write it in this sequence so that I won't start with the repeated eigenvalue. Non-repeated procedure is simple. So lambda 1 equal to 8. Equations will be minus 2, minus 2, 2, minus 2, minus 5, minus 1, and 2 minus 1 minus 5, x1, x2, x3 equal to 0, 0, 0. So minus 2x1 minus 2x2 plus 2x3 equal to 0. Minus 2x1 minus 5x2 minus x3 equal to 0. So it is x1 upon 2 plus 10, 12 equal to minus x2 upon 2 plus 4 6 equal to x3 upon 10 minus 4 6. So lambda 1 equal to 8. Capital X1 will be 12 minus 6 6, that is actually 2 minus 1 1. Here there is no difference, like for a distinct root there is no problem. And when the root repeats, then the problem might begin at lambda 2 equal to 2. We get the equations as 4 minus 2 2, 2 1 minus 1, and it is again 2 minus 1 1, this is minus 2. x1 x2 x3 equal to 0 0 0, and we find that the equations are just the same. So ultimately the equation is 2x1 minus x2 plus x3 equal to 0. So we end up here, and even if we substitute next time 2, it is going to be the same thing. Our procedure tells us that, well, let us assume one, say x3 equal to 0, and so we get 2x1 minus x2 equal to 0, or 2x1 equal to x2, that is x1 upon 1 equal to x2 upon 2 equal to x3 upon 0, and I get capital X2 as 1 2 0. So there is no change till this point. Previously we used to substitute something else as 0 when the matrix was not symmetric, and now the procedure will change. We will have to assume the third vector as LMN, and that LMN should be orthogonal to this and orthogonal to this. Got this? So we say that. Oh, repeat is karna remi. I'm just repeating it. I said that till this point there is no difference. Previously we used to assume something else as 0 and find the other two values, right? Here we say that as matrix is symmetric, the eigenvalues, eigenvectors must be orthogonal. Therefore, let capital X3 be LMN, and x1 x3 dash should be 0 and x2 x3 dash should be 0. So this third vector is assumed, and it should be perpendicular to this as well as this. So if we multiply, we get 2l minus m plus n equal to 0, and if we multiply this, we will get l plus 2m plus 0n equal to 0, and we again get two equations which are to be solved, and so it comes out to be L upon, so this was my previous thing, it will be L upon minus 2 equal to minus m upon minus 1 equal to n upon 5. And so capital X3 comes out to be minus 2 minus 1 5 plus 1 5. Is it orthogonal? 2 plus minus 2 plus 2 0, and over there it is minus 4 minus 1 plus 5 0. Now suppose we would have said that x2 equal to 0, then you will get 2x1 equal to minus x3, or x1 upon 1 equal to x3 upon minus 2 equal to x2 upon 0. So we would have got it as 1 0 minus 2. 1 0 minus 2, this is not orthogonal to this. So that nature disturbs. It becomes dependent. We don't want it dependent because the matrix is symmetric. So I said that we cannot follow the earlier procedure. For non-symmetric it works. For symmetric we will have to make a statement, assume the third one and proceed. Okay. So that's why we are required, whenever eigenvalue repeats, we are required to look at the matrix. If they are not repeating, we need not look at the matrix at all. The procedure follows. There won't be any trouble. Okay. So we first find the distinct value, its eigenvector. Repeated one we can solve by assuming as usual, and the second one we will have to assume, consider it as orthogonal and then solve. Today we will just continue with the matrices part, and hyperbolic we will do tomorrow. Right? Hyperbolic घ्यायचा आहे. Okay, solve one problem and we will go for orthogonal, hyperbolic. अरे तू नाही रे, पण बाकीचे आहेत ना. हां. Yeah, we'll solve one problem and then shift to hyperbolic functions, and let that problem be a simpler one. 2 0 1 0 3 0, and it will be 1 0 2. But remember the procedure for it.